Everybody get a copy of the notes? I think there's some extras over here, right? Thank you. Okay, we went over all these announcements last time. The fact that you are going to have a busy Tuesday. Lab 5 report is due at 11 o'clock. That's when we're going to do the Metacentric height lab. The Metacentric height lab uses that same floating pontoon as we used for the buoyancy lab, except for we're going to start playing around with the weights to get it tip over in the water to see how far we can tip it over before it capsizes. Also, at 2 o'clock, you're going to have your midterm exam, and so then that's when the homework assignment is due. So any questions about these announcements? We'll talk about the exam here in a minute, but schedule, questions? Okay. After we discuss the exam, we're going to talk about buoyancy and stability of floating bodies today. On the subject of the exam, though, you can bring 1 page of equations, front side only. That should be plenty of space for the number of equations that we've covered this semester. Now, what the equation sheet shouldn't be is a list of definitions of terms. I may have a conceptual question or two on the exam, but the equation sheet is just supposed to be formulas and defining the variables in that formula. Yeah? Either one's okay. So some of the big ideas that are covered on this first midterm exam, the exam is just covering the content from lectures 1 until today, and I think we're on lecture 10 today. We covered chapters 2 and 3 in the textbook during that time. So that includes fluid properties like density, specific gravity, and so on. It includes the ideal gas law, and we did some problems where we're looking at how much a certain volume of volume of air weighs. There are problems having to do with shear stress, shear force, viscosity. Remember the problem where we wanted to find out with the plate moving past another plate, what force is required in order to make that happen. There are questions potentially related to surface tension and how high a liquid will rise in a glass tube, or the weight of a bug walking on the surface of water. That also ties into surface tension. Vapor pressure is the idea that liquids have differing propensities to go from the liquid phase to the gas phase, and it's a temperature-dependent property. As temperature increases, water and other liquids come closer to their boiling point. When we started talking about pressure, we also talked about the difference between absolute pressure and gauge pressure. And remember that the difference between the two is what you're using as your datum. What do you call zero? And so when you're calling just an absolute vacuum zero pressure, that's absolute pressure. And when you're using some other reference like atmospheric as the starting point, then that's the definition of gauge pressure. Calculating hydrostatic forces from pressure is just the recognition that force is pressure times area. And so that came into play when we were doing pressure transmission problems, for example, like the jack, and finding out how much weight a jack can lift with a certain amount of force on the handle of the jack. The hydrostatic equation, we learned a couple of different ways to express that same principle. There's the full version of the hydrostatic equation, which has a Z1 term and a Z2 term. But then in the abbreviated version of the hydrostatic equation, we just called the difference between those two elevation values delta H. And so that delta P, the change in pressure, was equal to delta H times the unit weight of the liquid. Piezometer and manometers are both ways of measuring pressures or pressure differences. And we did some questions having to do with a U-tube manometer, where there's a manometer liquid different from the fluid flowing through a pipe. You also had some manometer problems in the homework. Piezometric head and piezometric pressure are different ways of expressing the same thing. It's just if you're dividing by pressure by unit weight, if you have pressure divided by unit weight, that's a head. And the units of this will be meters. And so a way of measuring pressure is just for a pipe with a piezometer, for example, the water level will rise to a certain height. That piezometer is a way of measuring pressure, but what we will call the distance from the center line of the pipe up to where the liquid is, we call that head because it's sort of like something the water's poking out of the pressurized conduit. Forces on flat surfaces, both the vertical and the inclined forces, I haven't written the exam yet, and I have some questions where the plate is vertically oriented and some questions where the plate is at an angle. And when the plate's at an angle, remember the difference there is that y bar is not going to equal delta h. But when the plate is vertically inclined, the depth to the centroid and the inclined depth to the centroid are the same. So be prepared for solving problems that may include a flat surface or a curved surface. But in the case of a flat surface, that flat surface may be vertically oriented or it could be at some sort of an angle. And of course, forces on curved surfaces, we've been doing that fairly recently. We break it up into its vertical and horizontal components is sort of the problem-solving strategy for that. And finally, what we've talked about last time, buoyancy, and what we're going to be talking about today, stability of floating bodies, all of this is fair game for the exam. So these are some of the concepts that we've covered so far in the semester. I got a good question about how should you study for the test. I think that if you've solved the homework on your own, rather than using another student as a crutch or using a solution manual as a crutch, if you really had that honest struggle with the material and were able to figure out the homework problems, and if when you had a mistake you figured out what your mistake was and you reconciled in your mind what's the right way to do it, if you've already been through that process, then you're already most of the way there and probably don't need a lot of additional study. So reviewing how to solve the in-class examples that we do, how to solve the couple of quizzes that we've had, how to solve the homework, I think that's probably a really effective way to study. And the textbook is also a great resource. It has several examples on almost every one of these concepts that we didn't have time to cover in class, and so you can reinforce in your mind the concepts by looking at what examples are in the text. So that's what I'd suggest. As you're preparing the equation sheet, what equation should be on there? Just the ones that you've used in the homework, really. Equations related to these big ideas. Yeah?
Are we using specific weights on there, like mercury, 20 degrees, or anything like that to get?
No, if it's a matter of fluid properties, I'd provide that for you. Yeah. The only one that I wouldn't provide is water. I assume that you've got that memorized by now. No, I won't. So you can take which equations from that equation sheet I previously gave you and you can copy it onto the one that you'll be using for the exam. Okay, so just as one more preparatory thing, let's revisit geometry and how to make sense of these different side views that we sometimes get. What is the length, what are the dimensions of this? It's a triangle that's submerged underwater, but what do the dimensions that are given us tell us about the actual size of the triangle? Because in the front view that we've got, we're looking at it this direction. And so what looks like 110 centimeters, that's not actually the height of that triangle. And so I wanted to reemphasize the importance of being smart about the geometry. We do actually know it's 95 centimeters from that front view. That dimension isn't warped. But the fact that we're looking at it and it's at an angle where it's 200 centimeters from the front edge to the back edge based on the way that it's oriented, this distance here we can find by saying it's 110 centimeters squared plus 200 centimeters squared, and then we take the square root of the sum of those two, and we'll get that it is 228.25 centimeters is the length from the top edge down to the corner of the triangle. So what looks like it's really only 110 centimeters tall, in truth it's much longer than that. So sometimes on these hydrostatic force problems, especially when it's a plate at an angle, the geometry of it can be as tricky as the actual hydrostatics. Let's take another look at buoyancy. We were talking about buoyant forces last time, and what is the buoyant force dependent on? What was the big idea? Submerged depth, all right. Yeah, how deeply it's submerged is going to depend on, you know, the force from above is going to increase as it gets deeper, but then again, so is the force from beneath. So actually the magnitude, the net magnitude of the buoyant force isn't going to change. The buoyant force is the same 1 meter under the surface as it is 5 meters under the surface, the net buoyant force. So the force up and the force down are both changing, but they're changing at the same rate. So it's the difference between the two. What we said last time is that F sub B is equal to F up minus F down. So the forces from below are pushing up on this more than the forces from above are pushing it down. And the difference between the two is constant, no matter how deep you get. So how do we calculate? What's the easy formula for the buoyant force? Do you remember that? It only has two parameters. Volume, that's right. Volume. Yeah, it's a submerged, right. So it's the volume of the object that's beneath the waterline. So if it was only partly submerged, then it's the submerged volume. That's good. It's important to distinguish. So volume, and I'll say submerged volume, because in the case of like an iceberg, the volume of the iceberg that's above the waterline doesn't count in the buoyant force. So volume is part of it, and what's the other part? That's right, unit weight. So that tells us what the buoyant force is. Now here in this one, we've got a barrel that's fully submerged. We know the diameter of the barrel, we know its length, and how deeply submerged it is. The fact that it's 5 meters under the waterline, that's maybe a distractor. Remember, we've talked about how sometimes you have data that you don't need and how deeply submerged it is. Since we can calculate the buoyant force just as the volume under the waterline and the unit weight, it doesn't necessarily matter that it's 5 meters under there. Okay, so the buoyant force, FB, is going to be unit weight times the volume of water displaced. That barrel is pushing water out of the way. Where the barrel is, water isn't. And so how much buoyant force there is equal to the weight of the water that got pushed out of the way by the barrel. The volume of the barrel is pi d squared divided by 4 multiplied by the length of the barrel. So pi 2 meters squared divided by 4 times 1.80 meters as the length of that barrel. The volume of it is 5.655 cubic meters. So the volume displaced, 9810 newtons per meter cubed, is our typical unit weight of water when no specific temperature is given. Multiplied by this 5.655 cubic meters tells us the buoyant force is 55,474 newtons. Okay, now the barrel has a mass of 1,600 kilograms. Will it sink or will it float? Okay, so the weight is going to be the mass times g. And the mass of it is 1,600 kilograms, and g 9.81 meters per second squared. So it has a weight of 15,696 newtons. So F sub B is greater than W, which means it must not be in equilibrium right now. If it's under the water line, it should float. Maybe this barrel was just released and it's beginning to float to the surface. It'll float. One other thing that we could do, one of the ideas that was introduced previously, is that you can calculate unit weight of solids just like you can calculate unit weight of liquids. So what if a question asked, what is the unit weight of the barrel? Well, unit weight is weight divided by volume. This barrel was 15,696 newtons over a volume of 5.655 cubic meters. And so it was 2776 newtons per cubic meter. So the other way to look at it is that the unit weight of the barrel is less than the unit weight of water. So that's another explanation on why it should float, is because it's less dense than the water. Buoyancy is pretty easy, right? Of course it is. Any questions about this example? Yeah.
When we want to observe the specific weight, we should not use the weight of it in the fluid. It should be out of the fluid if we want to do that.
The weight of the object?
For the specific weight.
So for the barrel, the weight of the barrel is the same whether it's out of the water or in the water. It weighs the same amount. But what you're thinking of is you're thinking, well, I weigh less when I'm in the water because you feel less force on your feet. You weigh the same whether you're in the air or whether you're in the water. It feels like you weigh less because the buoyant forces of the pool are lifting you partly out of the water. So the reason why it feels like you weigh less is just because the force on the bottom of your feet is lower, but you weigh the same. So here, it's not that the barrel weighs less when it's out of the water or in the water. We use the same weight to find the unit weight of the barrel. Okay, now here is a little bit of a homework help for the assignment you've got due on Tuesday. This is one of my favorite questions from the semester because it's a little tricky. But what I don't want you to do is get hung up on trying to visualize what this thing is. So what I want to tell you about is what this thing is and what it looks like. They've given you a side view, and then in the written description, it mentions that there's actually 4 of these barrels. It's like a floating platform. The floating platform looks like this. So here's a barrel, here's one. There's a barrel floating at each of the 4 corners of this structure that is held together with a truss. So we know how much the structure weighs. The floating platform weighs 30 kilonewtons. And then they also tell us that for every meter of length of these barrels, it weighs 1 kilonewton. So that if the total L, if L was 2 meters, for example, then that would mean that there's 2 kilonewtons of weight for each one of the 4 barrels. And so there's some total weight of the structure that depends on how long those barrels are. And they're saying, how deeply do the pontoons submerge for the floating platform to be 1 meter above the water surface? We don't want the actual truss, the structure, to be down in the water. So the longer we make the barrels, the heavier it gets. But then again, the longer we make the barrels, the more that can be floating underneath the water. And so this is an equilibrium problem where you're going to have to balance out the buoyant force and the weight. And of course, it's going to be floating, and so in this problem, weight will equal buoyant force, but both of these is going to have the same variable on both sides of the equation. On both sides of the equation will be the unknown length, L. So the weight depends on L, and also the buoyant force depends on L. What's the formula for buoyant force? Volume displaced times unit weight. So you're going to have to write some expression as a function of L that tells you what is the volume displaced. Now, unit weight is just water. But you're going to write volume displaced as a function of L. Okay, now the weight, we also know that the weight is as a function of L because it's 30 kilonewtons plus 4 times L, because it's 4 of them, and for every meter of length is 1 additional kilonewton. So that's the tip on how to do it, but really what I wanted to do is just show you that top view of what this structure looks like and acknowledge that it doesn't have 2 barrels, it's got 4. Yeah. It's neither. It's the volume of barrel under the water line. Yeah, so there is a difference between the two because if you look, L is showing you the 1 meter plus the length that's underneath the water level. So this will be as a function of L, but L isn't the same thing as how much is down under the water surface. Good question. Yeah, that's a tricky thing here, is that there's that additional 1 meter that has to be accounted for. Other questions? Oh, doesn't this look nice? I wish we were all sailing today. It's the SS Good Times right there. Those guys are going to have so much fun after their sailing is finished. There was a sailing club at one of the colleges I went to, and those guys had so much fun. They just sail all over the place, go to little regattas or whatever. It was really a drinking club, but they did it on boats. So what we're talking about now is stability of floating bodies. Now look at the difference between these two things. Both of these objects, on the picture on the left and the picture of the right, are floating part of the way in the water. So they're partially submerged. They're both cylindrical in shape, and they both have people standing on top. So there's some real similarities there, but it looks like he's having a hard time keeping balanced. He's doing all right. He's not in the water yet. Whereas these people, they don't seem to be having any trouble at all staying on top of the cylinder that they're on, the submarine. So why aren't these sailors dancing around and like riding the log like this kid is? Is it just because it's bigger, or is there something else there too? Why is it that a submarine stays upright instead of tips over? Center of gravity. What are you talking about by center of gravity? Very good. That's exactly it. Yeah, they don't make like the log. The log's center of gravity is in the center of the log. And so there's nothing to keep the log from spinning around. Its center of gravity is right here. So that if now all of a sudden you're standing on top of it, if you put a little bit of weight that direction, like if you lean on this side with your foot, it's just going to go ahead and spin. But the submarine, they intentionally put a lot of ballast down here at the bottom, and so the center of gravity is down here, so it's a little bit more stable. If you lean on it this side, it might move the center of gravity this way a little bit, but it's going to want to go back to its neutral position naturally. So that's exactly what's happening. Now, look in this diagram, it's showing the case of the submarine where they've put a little extra weight at the bottom, and G stands for the center of gravity. C stands for the center of buoyancy. Center of buoyancy is same as the center of area. In this case, if it's a cylinder, then the center of area is going to show us the same place as the center of buoyancy. All of the forces that are acting on this circle are through this centroid. So if we started to tip it, this would be stable because if you roll it over, it will naturally right itself. It wants to go back to the condition where the weight is at the bottom. And that can be illustrated by looking at when you start to tilt it, where is G and where is C. So this is the log that is neutrally unstable. It's neutral. It's not that necessarily it's unstable, but it doesn't have any preference for being oriented one certain way. But now here is the submarine kind of case, and if you turn it so that the weight isn't at the bottom, think about the direction that each of these forces is acting. G is acting down, C is acting up, but since G is to the right of the center of buoyancy, it has what's called a righting couple. It wants to right itself so that it's back into the correct right orientation. And so if you have a piece of paper and you keep your finger on one side and then you push down on the other, like this is, you can think of it as G is one finger, C is the other. If you're holding it steady with C and you start to rotate that down with G, it is going to just naturally right itself until it gets back into the stable position, like is indicated with figure A. So boats are designed so that they have that same righting couple, so that when they are outside of the straight up and down position, that they will come back to the neutral position that they are originally in. So this is an exaggerated case. Boats don't always have the same stability to the extent of this, but now we have a center of buoyancy and we have a center of gravity. In this case, the center of gravity is above the center of buoyancy. So it's maybe not going to be quite as stable as the last slide we were looking at. In this case, when the center of gravity is below the center of buoyancy, it's going to be super stable, very, very stable. But even in the case of this boat, we can, just by being smart about it, we can make it stable even though the center of mass is above the center of buoyancy. And so what do I mean by be smart about it? The ships are designed naturally so that the center of buoyancy will change depending on how tipped over it is. That's why it has this shape of the hole that it does, is because when it starts to tip over, the center of buoyancy is going to change actually. So if the ship tips over, C is going to move. The center of buoyancy actually shifts. So now take a look at this tilting ship. When it tipped over, this part of the hull is deeper under the water. And since some of the hull on this side came out of the water, the center of buoyancy isn't in the center of the ship anymore. The center of buoyancy went over towards the right because more of the shape under the waterline is on the right side of the boat. And so now the center of buoyancy shifted over, and again we have that righting couple. We have center of gravity, which didn't move. As long as the load is secured, it might be all the people, like, did you ever see WALL-E? Like, WALL-E is a lot like being on a cruise ship in terms of the types of people that go on the cruise. At least that was my experience. So if the ship starts tipping over and all of the passengers get on this side, maybe it'll tip over, but maybe not. It's not supposed to. If the load is secure, then the center of buoyancy will shift to the right. The center of gravity stays the same, and so it is going to tip it back to its neutral again. So we now have a new variable that's defined here, M, metacenter. And metacenter is where the center of buoyancy is always going to point at. And what you'll notice is that when the ship began to tip over, the center of buoyancy is still pointing up, but it points to this M. So that if we tipped it over even more, then C would now be over here, but C would be pointing towards M. M is this location where as you tip it back and forth, C is always pointing at M. And so that is going to be an important thing that we're going to have to measure is these distances. We're going to measure the distance between the center of buoyancy and what's called the metacenter, M. So ships are designed specifically so that they don't tip over. And we'll do some calculations that look at that. What you know for stability, the criteria for stability is that M has to be above G. If I give you an exam question, I may give you the dimensions of a barge, something like that, but what I wouldn't tell you is the way you know it's stable is that M has to be above G. That's something that you need to remember or just know is that stability, this ship is stable because M is above G. The metacenter is higher than the center of gravity. If G is above M, then it's not stable. If your center of gravity, like if this is really if it's top heavy, if instead of having a lot of ballast at the bottom of the ship, like if they moved all the heavy stuff to the top of the ship, obviously that's going to be really tipsy and it's going to lend itself to less stability. And so if we move the heavy load from down below the waterline, from the hull up above, then essentially what you're doing is you are changing the center of gravity to above the metacenter. And that's what you want to avoid. You always want to make it, in ship design, all the times you design a ship, make sure that you put the center of gravity below the metacenter. So here is some of the ships that we have coming through the tri-state area, barges. Actually, you may not realize it, but Huntington is the largest port in the United States in terms of the mass of cargo that's onloaded and offloaded. Huntington has more tonnage of cargo moving in and out of the area than any other port in the United States. And the funny thing about it is, yeah, that's a point of pride, right? Bigger than the port of Los Angeles, bigger than the port of New Jersey. Any port in the United States, they do a lot of volume, but Huntington's got the most mass, and it's because of all the coal that gets loaded and offloaded in the area that's considered the port of Huntington. There isn't one single like dock. It's not Harris Riverfront Park or anything like that. It's just that, you know, there will be, AEP has a terminal for offloading and onloading coal. Probably CSX has its own terminal. All the different companies that are along the river, scrap metal concerns and so on, they have their own little floating dock where cargo will come in and go out, and that entire length of the river is called the Port of Huntington. So here, what this is showing in this figure is the dimensions that you're going to have to know in order to calculate stability. We're again going to have to return to the idea of area moment of inertia. Now, area moment of inertia for a rectangle, like this rectangular barge, is the dimension of the length and the width, B. B is the width, and how you know what is A and what is B, just whatever the boat looks like, B is the shorter dimension. And so if it's a ship like this, then you're in trouble, number one. But B is the width dimension, and A is the length dimension. Okay? Boy, it's a bad ship. So, again, the criteria for determining stability is you want to calculate something called metacentric height. And so you want to know how far away is the distance I, area moment of inertia, divided by the volume, the submerged volume of the object, and that's what gives you stability. And then what gives you instability is how far above the center of buoyancy is the center of gravity. So if GM is positive, then the ship is stable. So look at the figure here. A big CG makes your ship unstable. So look at C and where G is. If you have G really high in the boat, like if G was up here, then you're going to have a big CG, then that would give you potentially a negative value for the overall expression of GM. But what gives you stability is a big wide barge. Like, look at this barge. It's not tipping over. Look how wide it is. It's very, very wide. And it's shallow, too. So that means there's probably a really small CG on a barge. Because it's so shallow, there's very little chance that they could load that coal very high up above where the center of buoyancy is. And so in the case of the barge, what makes this so stable is that you've got a big area moment of inertia. I is going to be enormous. And so I is what's going to tend towards a positive value. And the CG is going to be small for a barge. So let's take a look at this with an example. This is another one of those activities I'd like you to attempt with a classmate. And in fact, you can get together with up to 3 students. And I'm going to be giving every student one of these. But write your name first, and then the other people you work with on the paper, and then I'll just collect one of these per group of students that are working together. I'm going to have you take a crack at this independently at first and see how far you can get in about 15 minutes. And then I will start in on the solution and do the rest of it for you. But I am going to collect it at the end of class. Even though I'm writing the solution as you're working on it, I'm still going to collect it because I just want to give credit to those of you who are here today and make the effort to transcribe and try and solve the problem. The thing you can't do on this today is work alone. You have to work with a partner. And the reason why, even though you may be able to figure out on your own, I want you to share the wealth. I want you to help explain it to another student if you already do. No, and if you don't know, I want you to help learn it from a student. While you're working on that, I'm going to hand back the labs. I got the labs back from Patrick. He continued to grade the labs. He suggested that if you have questions about the lab grade or any of the comments that he's written, that he'd be happy to talk to you about it if you're not sure why he deducted, so on. I will tell you, though, that he used the full rubric for grading this lab handout, and so this should give you an idea of what he thought was strong on the report, what still needs to be improved, and so on. So the 2 things is, if you've got questions, he's happy to talk to you. And take a look at the rubric in addition to the comments on the lab itself. Okay. With that said, go ahead and get started on this in-class exercise. Did everybody get a copy of the handout? Okay. What's that? Oh, wait, yeah, because it's above 0. Yeah, that's the criteria, is above 0. Good question. Yep. Since GM greater than 0, then we can draw the stable conclusion. Yep. 2 different clickers, that's not one. All right, so I was really impressed. Everybody seemed to come right at the finding D pretty easily. So I think you've got the buoyancy principles locked down. I is a little tricky just because it's hard to remember what is the width parameter and which is the length parameter. But we need to cube the shorter of the dimensions in case of a stability of floating bodies. We want to find it. Think about what is the risk of it rotating. Is this barge going to be more at risk of turning over sideways or turning over end? It's not going to capsize, like accidentally tip over frontwards or backwards. If it's going to capsize, it's going to turn side to side to capsize. And so the critical component here is the width. So we're cubing the critical component, which is that 6-meter width of the barge. Find the volume displaced, just the volume underneath the water line. So any questions with the preliminary stuff? Now it's the geometry of it, finding the location of C and how far it is from C to G that is the heart of the matter. And the center of buoyancy, C is defined as the center of buoyancy, and so it depends on how much is below the water line. And so since we know D, just by inspection, we can tell that the center of buoyancy is going to be half of the submerged depth. And so we can find 1/2 of D, and then that tells us the dimension of from C to the water line is 0.989 meters. And then this other distance from G to the water line we get as the difference between the 2.44, the total length of this dimension, minus D. That's where this comes from, G to the water line of 0.462 meters. And so CG is just the total distance apart. So you think of this is top heavy, right? We know it's top heavy. Look at that load sitting there on top of the barge. They're saying the center of gravity for this barge is above the water line. So why doesn't it tip over if the center of gravity is above the water line? As it starts to tip over, what happens to prevent this from becoming a disaster? C moves. That's the easiest way to say it, is as it starts to tip over, the center of buoyancy, if it tipped over this way so that the right side is getting deeper, the center of buoyancy would shift over here, and then all of a sudden you've got the forces acting up, the gravity acting down, and it would tip it back over again. So it's only going to capsize if there's some sort of a force that's larger than that righting couple that's always trying to get it shifted back into stability again. And so what makes it stable is the fact that the forces that are overcoming the tipping, the area moment of inertia divided by the volume, this is what resists it from capsizing, is greater than this long distance CG. A big CG makes it riskier and riskier that it might tip over. The length CG is what is the parameter that's making it closer to capsizing. What makes it stable is a big I divided by B. And in this case, we have an enormous area moment of inertia because it's such a wide, shallow barge. So, any questions about this example? In-class exercise, I should say. Okay, we've got one more slide to go over, but what I would like to collect from you is just 1 page per group. I'm going to give you each some homework points for the work you've done today in class. Make sure that you've got the name of everybody that you worked with, and then when I return it, I'll return it to whoever's name was first on the page, and the rest of you can keep your paper. So I only need to collect 1 per group. All right. So let's look at this last slide unless there's any questions about this one. All right. We have an example where there's a curved gate. Curved gates are tricky, so I thought just as one final illustration to give you before the exam, we'd take a look at a tricky curved gate like this. We know that we solve curved gate problems by considering the vertical projection of the surface and then also the horizontal forces. And in the past, those horizontal forces have been the weight of water above the gate. So here's a curved gate. It's a curved gate. How much water is above that gate? None. There's no water above that gate, but there is going to be a vertical force because of that gate. So I'll give you a minute to think about what's going on here where we've got atmospheric pressure, and what is the water pressure that's touching air? It's 0 right here at the interface of air to water. The pressure is 0. So if the pressure here is 0, What's the pressure here? Also 0. Okay, so we've got 0 pressure and zero pressure. And hydrostatic equation says that when we go up through water, the pressure decreases. So 0 pressure, how can you get lower than 0 pressure? What's that? It's like a suction, right. But I thought that pressure only went to 0. How are we going lower than 0 pressure? Negative pressure. It's a vacuum. So when we said it was 0 gauge. It's not 0 absolute here. It's 0 gauge. And so here we're at 0 gauge, and now we're at a negative gauge pressure. Now it's not negative absolute pressure. Hopefully not. Otherwise the water will start to cavitate. But as we go up, the pressure is decreasing and decreasing, and so actually this gate is being sucked downward. That's the vertical force, is it's being sucked downward. So in the past, what I've told you is the vertical force depends on the weight of the water above it. So make the intellectual leap. How would you guess how you can find the vertical forces in this problem? If previously it's been the weight of the water above the gate tells you how much vertical force you need to resist that, what vertical force is required to hold this system steady? Pressure times the area. It could be that. Remember, there's going to be a lot of different pressures because this is a curved gate. So the pressure here is different from the pressure there, and the pressure there, and the pressure there. So integrating those many different pressures can be done, but there's actually an easier approach.
The depth of the water above the water line.
Ah, okay, so you're saying, let's think about the water line. Let's extend it over, and how much water is above the water line? And that's exactly it. Very good. So we would say, well, we've got 1 foot of water here, and then we could calculate, like, what's the volume of water in this quarter circle, so that if you find the weight of the water above the water line, that tells you the equivalent vertical force that's getting pulled down on the gate. Now that's just the vertical force. There's also a horizontal force. Now when we've had curved gates, how have we found the magnitude of the horizontal force? Projection. Exactly right. So here we've got a gate that's 2 feet wide, and it has a radius of curvature of 3 feet. So now if we think about what does the shape of that gate look like, it looks like this, where it is drawn poorly. It is 3 feet tall and 2 feet wide. That's the projection. So we can find the magnitude of the force by simply saying, well, we've got a vertically oriented gate, and we want to find the pressure at the centroid. We want to find the area of the plate. And there is a pressure on the gate, but it's just that it's a pressure that's 0. It's below 0. It's a negative gauge pressure. So that the horizontal forces are going to be, let's break it up into parts. Now that we've talked about the concepts and sort of a problem-solving strategy, the execution is next. And, you know, talking about partial credit on the exam, I give lots of partial credit on exams. Like, I understand that mistakes happen, and in the rush of the moment you may not be able to triple check your calculations like you otherwise would like to. So if you get the basic structure of the solution right but make a few calculation mistakes, you may get more than 2/3 of the points available, you know, if your problem-solving strategy is sound. And so here, even though it's bizarre, the fact that we've got a negative pressure, if you set it up like saying, curved gate, I know I'm going to find the pressure at the centroid and a projection of the curve in order to find my horizontal force. The vertical force depends on the weight of the water either above or below the water line. If you can show that you have that understanding of the procedure and the fundamentals, then I can be more charitable as I overlook calculation mistakes on the final execution. So horizontal force is what we keep in our mind is vertical projection. Okay, and so the horizontal force is the pressure at the centroid times the area. It is delta H times the unit weight times the area. Okay, so delta H is actually going to be negative 2.5 feet, because delta H, the definition of delta H is how far below the water line is it to the centroid. So delta H, just the definition of delta H, assumes below the water line. In this case, we are above the water line to the centroid. So the centroid of the projection is 1.5 feet from this edge up to the centroid, and then the additional 1 foot from the point that's shown to where the water line is. So that's why it is negative 2.5 feet. Negative because we're above the water line instead of below it. That negative sign is what's going to give us the negative pressure, ultimately. This liquid isn't water. It's just some liquid that has a unit weight of 50 pounds force per cubic foot. So we'll put in the unit weight of 50 pounds per cubic foot. And then the area of the plate is 6 square feet. The hydrostatic force is negative 750 pounds. And so instead of being a force that's pushing on the gate to the side, you know, towards the left, it's actually sucking the gate towards the right. It's pulling the gate inward at the magnitude of 750 pounds. Any questions with that so far? Okay. Then the vertical force, sort of the thing you should keep in mind for vertical force, is weight of water. Well, it's not water, weight of liquid. Okay, and so we need to find the area of that quarter circle and the area of the rectangle beneath it. The area of the quarter circle is pi r squared divided by 4, since it's a quarter circle. So pi 3 feet squared divided by 4, 7.069 square feet. And then element 2, that rectangle that's beneath it, is 1 foot by 3 feet as the area. So that's 3 square feet. So the area, the sum of the area, the two pieces together, is 10.0686 square feet. And then the volume is area times the depth into the page of 2 feet. So we can find the volume is 20.137 cubic feet. And then the vertical force, F sub V, is just going to be the weight of the water. So it would be the unit weight times the volume. The unit weight of this liquid is 50 pounds per cubic foot. And then what we just found was the volume is 20.137 cubic feet. So the vertical force is 1006.9 pounds. And that force is going to be downward. There isn't necessarily any sign built into the formula that would tell us it's going to be downward. I guess we would have to just sort of add that in, knowing that if it's above the water line, there's a suction, and the suction is pulling down on the gate. So I just wanted to throw that example in there, not as necessarily foreshadowing that the exam is going to have some crazy shape like this, but just to refresh your memory of the basics of a curved gate and then how it can be applied to what seems from the outside a pretty unfamiliar type of problem. That's it for today. I'll see you on Tuesday for our big day. Remember, we've got the lab during 11 o'clock and then the exam at 2. Make sure that I get a copy of that in-class exercise so I can give you the credit for it. Just in a pile over there on the table.